Good evening, everybody. Could you see the special announcement as well as do you hear from me? Please answer and make response in the chat room, please. Can you hear from me? Can you see the message, the special announcement? Please reply me. Okay. Thanks. I think I better start right now, okay? Now, here's the special announcement. Now, there will be no midterm test in this semester for this course. The assessment will be reinforced with the following measures in terms of the continuous assessment. Now, apart from the assignment 1, 3, and you have to hand in the assignment from 5 to 10, right, in order to make up the midterm test. So you are required to submit right now, right, from the assignment 5 up to assignment 10. And the laboratory reports shall be submitted by individual of yourself, right, rather than the group work. Of course, the assessment weighting will be adjusted to replace the original coursework schedule, but this will be announced shortly. Okay, is that clear? Is that clear? Everyone has got the message? Yes or no? No, there will be no midterm test. Is that clear? But you have to hand in the assignment from 5 up to 10. In other words, you have handed in the assignment 1, 3, and from now on, 5 up to 10. Okay? That's all the assignment you have to hand in and will be counted towards your CA score. Somebody cannot see the screen? So can you all see the screen right now? Okay, any question about for this special announcement? Any question? Is that clear? If no question, I will continue my lecture for this evening, right? So slope stability. Okay. Now, for this slope protection. Now, after we have talked about the slope analysis, right? The stability of the slope, whether it will sliding down along the slope onto a road or even towards a house. Now we have learned about the analytical methods, right, for the analysis of the slope, whether it's safe or not. Now we come to the slope protection. Now what's the slope protection? It's going to protect the slope and reduce the slope against deterioration or becoming worse and worse, right? Or sometimes it's called the erosion of the slope. Now, there are two major methods of the protection. First of all, you have to protect the surface of the slope, and also you have to install the drainage measures. What's drainage? It means to drain the water away. Of course, the water may come from the, from the rainfalls, or even from the groundwater, right? The water inside the ground, right? Or the behind the slope. So you have to provide the drainage measures, right, to carry or to discharge the water, whether running on the top or from the interior of the slope as far as possible. The Geo Guide 5, right, is published by the Geotechnical Engineering Office of the CEDD. You know CEDD? The Civil Engineering Development Department, right? CEDD, Civil Engineering Development Department. Right? Now, the Geo Guide 5 recommends different kinds of the slope protection measures, and they should be included in your maintenance work. That is, in the slope maintenance works. You have to provide the, the surface protection, to apply a impermeable surface layer on the slope surface, or you have to install the surface drainage or the drainage behind, right? Behind the surface covers, right? The rigid surface covers. And also the subsoil drainage, right? The discharging away of the groundwater from the interior of the slope mass. Now, the surface protection. You provide a surface layer, right? A surface layer. What surface layer? Here. Here's the surface layer. Surface. The surface of the slope, right? You can see there's a layer of different materials, right? You can have a good range of the different materials, right, to be applied to the slope surface, such as, you know, the shotcrete. What's the shotcrete? Shotcrete means shooting the concrete, the wet concrete mix towards the slope surface. Spray concrete. Okay. Spray concrete, 噴射混凝土. And also the chun lamp require an old material, right? Now almost obsolete nowadays. 豬欄, chun lamp. And also stone pitching, right? Stone pitching means you apply the, you know, individual stones and packing on the slope surface, and then joint the stone pieces with the cement mortar, right? So stone pitching. Oh, and you can also apply the geosynthetic material. Geosynthetic material. It means the, you know, the synthetic material coming from the, you know, plastic, right? Some plastic. They are usually plastic. Plastic. Gargan okay? Geosynthetic material. Or sometimes you may have prefabricated units. Okay? You know, the precast concrete blocks, right? Precast concrete blocks could also be used, right, for the slope protection at the surface. And of course, you may apply the vegetation. The vegetation. Planting the grass, right, over the slope surface, or even planting the trees or the shrubs, you know, the small and low trees, right? Low trees, or sometimes called shrubs, right? And also you may apply the hydroseeding. You know what's hydroseeding? 噴草啊. Okay. Now, when you develop and install the vegetation on the slope surface, and you no longer need too regular maintenance for this slope, so it could be a very good and green and also aesthetic, right, appealing measures for the slope protection. Or you can, you know, you blend or you mix different types of plantation, right, so that the environment, right, could be more pleasing to anyone, right? So that is the a very good and green measures, right, for this kind of slope protection. Now, now we come to the surface drainage. As far as this surface is impermeable, that means the water cannot penetrate into the slope surface. So any rainwater, so the rain falling down on the slope, what will happen? Because it's not permeable, so the rainwater will go along the slope surface. We call this is runoff. It's a runoff, right? The rainwater falling on the slope surface will be running along the gradient, right? Along the sloping surface of the slope. So that is the surface water, right? Surface water, surface runoff. Sometimes it's called the surface runoff. Okay? So you have to install these surface channels to intercept. You mean to catch all the surface runoff, right, into these channels, and the channels will bring the water right downwards to the public, the storm drainage system, right, and then it will come to the storm water drains, right, of the public sewerage system, right. So that is the the history of any rainwater falling on the slope and to be carried away or to be discharged away through the surface channel until they are collected in the public stormwater drains. So that is the arrangement of the surface channel, right, to intercept the rainwater falling onto the slope surface. Now, of course, you have to minimize, right, the blockage. Now, any debris, the rubbish, right? If the rubbish or the debris are collected and stay in this surface channel, now the draining of the rainwater away will also be blocked. So that will upset the original purpose of our surface channel as designed. So you have to improve the surface drainage channel, right? Now, by regular maintenance of the surface channels, it means that you have to clear, right, all the debris, right, regularly along your surface channel. That will minimize the spillage of the surface water. In other words, if there is the the debris, if there's debris here, right here, stay inside the surface channel, and you have not cleaned, right, or clear this blockage, the surface water, right, will spill over this channel, and then it will go down all the way down the slope. And also you have to increase, right, the gradient of the channel. Whenever you increase the gradient of the channel, it means that the channel at the steeper slope, right, that's the gradient, then the water will be discharged much faster. So you have to increase as far as possible the gradient of the channels so that it can convey the water or discharge the stormwater right away, right? And that will keep your slope surface dry as far as possible. Now, to prevent the failure in the slope due to the seepage flow. You know what's the seepage? Right. Here. Say here, right? So rainwater falling on the, you know, the top of the slope. Now this rainwater may seep, right, into the slope interior. So you have to provide a rigid surface cover, right? So you can apply, you know, a rigid cover, right? Cover this so that the rainwater cannot penetrate into the slope. So you have to provide a rigid surface cover of the slope, right? And you could also to install the synthetic composite drainage material behind the rigid cover. In other words, you could have that sort apply, not a rigid cover, it's not a concrete layer, but you apply, you know, the synthetic. So any rainwater, right, falling on this, you know, that is a synthetic, right? This is the geosynthetic membrane, right? So any water falling down on this synthetic membrane will be collected, right, and discharged right, and discharged down the slope, right? And there the water will not go downwards, right, or will not go vertically deep into the soil mass, but it will be draining away along this geosynthetic membrane. So that is the purpose of the geosynthetic composite drainage material, right? Of course, the, you know, the synthetic membrane, geosynthetic membrane will have their own what we call the pore size, large to small, right? Pore size. So it is purposely, right, fabricated and designed with different pore sizes, ranging from small pores to large voids, so that any water could be collected and filtered and discharged, right away. And that will minimize the building up of the water pressure. You know, if you do not install that sort of the, you know, the rigid surface covers or placing any, you know, geosynthetic material, eventually the rainwater will, you know, if there is no such protection, what will happen? This rainwater will go downwards, and then you have what? The groundwater table will what? Become higher and higher, right? Until what? You know, fail, right? Slide down, landslide. So that is the purpose of the, you know, applying a rigid surface cover. So any question? Are you happy with the explanation for this slide? So you understand my explanation? Yes or no? Good. Okay, and now I continue, right, for the slope protection. Now here we come the subsoil drains. What's the subsoil drains? It means below ground level, right? Subsoil drains. Now you can see here, Okay, here, that's the subsoil drain. In other words, for any groundwater, right? For any groundwater, you want the water, right? Any water, say here, the groundwater table here, right? Now, when the groundwater become higher and higher, so what will happen? The water, right, will eventually be, right, go through this subsoil drain. Okay, you know that's the groundwater. GWT, groundwater table, right? You know, in the dry season, the groundwater table may at this position. So at dry season, right? Dry season. And in wet season, right? Here, the wet season. The groundwater may go up, right? Wet season. So in wet season, the groundwater table will go up, and then you will have your water coming out of your subsoil drain. Okay, this subsoil drain. Okay. Now, if the drain is installed nearly horizontal position, right? That is called the horizontal drain. Very famous, right? Horizontal drains. In other words, to allow the water, right, go out of the soil mass interior. Now, this is the subsoil drain. Any drains installed inside the soil, right, is called the subsoil drain. It's the, you know, it's an opposite measure to those surface channels to collect the surface runoff. But for groundwater, right, you have to install the subsoil drain. So that's the major difference between the surface drainage and also the subsoil drainage. Now, when you have installed the subsoil drain, you will have to put your subsoil drain as deep, right, and also as interior as possible, so that you have to collect all the groundwater seepage, right? Once you have removed all the groundwater, right, and let the groundwater go out, coming out, then the groundwater table will be lower, right? So in other words, you could have installed here, right? You may have installed this, you know, subsoil drain, right? So you have allow more water, right? So you have allowed more water coming out. So eventually, your groundwater table, even in the wet season, it will go down, right? Up to here. So you have the groundwater table up to here. So in the wet season, you know, the original ground table here, right? And now because of the installation of your horizontal subsoil drains, then the groundwater table will go down, right? because you have installed several layers of the horizontal drains. So that will increase the stability of your slope. So here are the, the surface covers. You can see here is the, that's the socket. So that is the socket. So spray the wet concrete on the surface. Spray, spray, 噴射. Spray the wet concrete mix on the surface. So that is the socket surface. And that's here's the, the green vegetated slope surface. And you have the chunam, very old style. It's now no longer used nowadays. So chunam is obsolete, right? Very old, like chunam. And here is the stone pitching, right? You can see the, the stones here, right? Stone pitching. Individual stones are packed together and joined with the cement mortar. And here's the subsoil drains. So if you have surface runoff, too much surface water run over the slope surface, and if the rainwater, right, stay for the slope surface for a long time, it will start what we call this erosion, right? The erosion. The erosion. Right? Soil erosion. It means individual soil grains will be carried, right, away by the water, right? So for years to come, so a lot of soil has been eroded away. In other words, the soil particle will be transported, right, from one place by the water to, right, down to the, the surface channel or even into the public sewer. So that's no good. We try to make the soil stay there, right? There should be no erosion. There will be no cutting away of the slope in any parts, right? So we have to stop the soil erosion. That's why you have to properly maintain your slope surface. So surface drainage is definitely a good measure, right, to stop the erosion. Right? So that will reduce the, the infiltration. Right? In other words, if the rainwater is allowed to seep in the soil, what will happen? This layer close to the slope will become very wet, right? Wet zone. So that is the process of the infiltration. And if during a very heavy rainstorm for a few days, what will happen? The wet zone will become deeper, right? And that will make the soil very saturated and wet, and you have loss of cohesion. So landslides, right? Landslide may occur, right? Because the infiltration of the rainwater, right, deep into the slope surface, so that the layer of soil close to the, the slope surface will become wet and lose their cohesion or lose their shear strength. and that will trigger a catastrophe landslides, right? So the whole soil mass may come down. So the slope drainage design aim at to collect the the surface runoff, right? Surface runoff from the slope, and we direct it to the convenient points of discharge. And you have to design very carefully those surface drainage to meet the given slope geometry, right? Depending on the slope geometry, you have to install different surface drainage system, right, for your slope. And you can see here, right, a U channel. That's a U channel, right? So you have to adopt, right, the slopes surface. So the left-hand side is a bit short, and the right-hand side is a bit high, right? That is the U channel, right? U channel. It's open, right? Not covered. So there's no open concrete U channel. Sometimes you have the half round channel, right? What's half round? Means that, right? Half round, right? It's a semicircle, right? Half round. Instead of U, U is like that, right? You got right here, and then you have a, consists of two parts, right? A half round channel and with two vertical sides, that is the U channel, right? Here's the U, and here's the half round, right? Half round channel. Now we use a lot of U channel rather than half round, because U channel will give you a bigger discharge capacity. Well, for the subsoil drain, of course, it helps you to discharge water from the interior of the soil mass or behind the slope. So it could improve the factor safety significantly by reducing the groundwater pressure, as we have discussed in the previous slides. Now, the subsoil drain may take in different forms, right? Here, you've got the horizontal drain, the drain galleries, right? And cut off. What's that? Say here, here's the slope, right? Very high slope. You can have the, the horizontal drain. Here's the horizontal drain. So any groundwater coming from the back, right, will be discharged away, right? Or you have the drainage gallery. Here's the drainage gallery. Okay. So the drainage gallery means a tunnel, right? Some sort of tunnel, right? You have packed some stones, right, all around, or even concrete, and then you have the water inside. So that's the water, right? It means the water will be collected by this, right? It's all the groundwater will be seeping into this tunnel, right? The drainage gallery. So that is the drainage gallery, right? And that is the drains, horizontal drains, and that's the drain gallery. So it's much more effective, right, with the drainage gallery. Why? Because the groundwater, right, will be lower, right, okay, the groundwater table will be much lower, right, by this gallery. Right? Okay, but of course it's much more expensive. And also you could have the vertical drainage wells. What's that? Suppose you have this well, right? You make this well, you know, 井, huh? Well means. So you have install, right, this well. So the water, right, will be collected. Okay, suppose you got a pump there, right, a pump. So the water will be pumped away. Okay, so this is the vertical drainage wells. So any water collected in this well will be pumped and discharged away. So that is the vertical drainage well. So what will happen to the groundwater table? We believe that the groundwater table right, WT will be lower down, right, by these drainage wells. And also you may have the cut-off wall. What's the cut-off wall? Suppose you have a slope there, right? And you have, you know, the original groundwater table from here, right? So you're worried about if the slope may be sliding down. So what you're going to do is to make a cut-off wall. So there's a cut-off wall. So the groundwater table on the right-hand side is kept there. And you have to install, right, up to an impermeable layer, right, impermeable. So the groundwater here, right, the groundwater cannot seep through this impermeable layer because it's impermeable. So the groundwater table behind this cut-off wall will stay there. And here on the left-hand side, what will happen to the left-hand side? It's completely dry, right? So you keep the soil mass of your slope completely dry by this cut-off wall. Right? That is the cut-off wall. Cut off, right? So, are you happy with the explanation? Any question? Any question? No question. So all of you are happy? Okay. Drainage of slope. Okay, now you have to know this word. Perforator. It means that you got many holes there. Perforated, right? It means a drain where the surface have many holes or slots, right? So that the water, right? The water could go into this horizontal drains, right? You have to allow the water to go in the horizontal drain. Otherwise, the horizontal drain is completely ineffective, right? You have to allow the water to go in, right? So that is the perforator. Or sometimes you have the slotted casing. What means slotted? You have this slot, right? Slot. So the water could go through these slots, right? Perforated or slotted casing. Okay? And it's recommended a filter be used along the drain. You know what's a filter? You know what is the purpose of the filter? Now, let us discuss about that. So you got holes, right? You got so many holes. Perforated tube. So the water could go in there, right? Okay. These are solids, right? And the solids. But if you have, the soil particles around your horizontal drain, now what will happen? Now, let me enlarge, right? Okay. When the groundwater, right, goes through this, right, here, and go into the perforated horizontal drain, what will happen? Eventually, there are small particles, right, carried by the groundwater will fill up this space. So eventually it will be blocked up by small, right, soil particles. So we have to stop that sort of the problem, right? So what you're going to do is to place, right, some filter here, right? Right? Okay, what's that? The filter layer. That's the filter layer. The filter layer. So that is the word, right? Filter. Filter is used to prevent any small particle blocking up the voids, right, within the soil, right? So that's the purpose of using a filter, right, to prevent any erosion, to stop the continuing carrying of the small soil particle, which will clog up, right, block up the voids in the soil mass. So that is the purpose of using a filter, right? Drainage galleries, I have talked about that, right? It's in fact a tunnel, right, which will be used to lower the groundwater table, course, the cost will be very high, drainage carry. And here's the, the vertical drainage wells, right? You can see here, you have to pump the water, right, out of the watering well. So after pumping, the original groundwater table will become that. The groundwater table, right? Or even, right, the groundwater table will be lower, right? Or even, for the best result, the GWT, right? And here, right? So the original groundwater table, right, has been lower, right, to a much deeper level. Now that will make the sliding of the slope becoming less possible, right? So here, right, because the groundwater has been lower, so the failure of the slope is become more impossible. And cut off, here's the cut off, right? We'll talk about, right? You can have, a impermeable wall, right? Now here's the impermeable wall, right? And if there's impermeable foundation under that, so this cut off, right? This cut off wall. Now, the actual construction of the cut off wall could be looking like this one. You can see the upper part is the compacted fill, so it's very dense. Okay, and then you have the, the perforated drain, the perforation. So, and then you have surrounded with, the you can see here what of the polythene, right? Polythene sheeting, impermeable, right? And then you have the, the filter material, the filter. What's the filter? It's the granular filter, right? What's the best, the filter material? A good selected range of large to small, particles, right? And well packed. So it's a specially designed, right, mixture of the, the aggregates, of the stones and the rocks and sand, right, ranging from large size particles to very small particles, and that will pack all together, right, in a proper way that will give you a very good filtration, that is preventing the small particles clogging up all these drains, right? No clogging, right? No clogging, but only the groundwater, right? seeping through this filter and go into the horizontal drains. So that is the purpose of the, the cut-off. Right? First of all, you have the impermeable, right? Polythene sheeting, and then you have the filter material, right? Fill all around your horizontal drains. Of course, the cost could be quite expensive. Right? Now we come to a very expensive measure, right? To prove slope by means of mechanical methods. In other words, you apply the force, right, to stop or to arrest any movement of the soil, right, for a cut slope, a very high cut slope. So let's take a look at that. Suppose you have a very high slope, then you're worrying about there is a possible, landslide for this slope. So you have to provide the anchorage. Okay. So when the slope is going to move, so if it's going to move, what will happen? This will provide a supporting force, right, to stop that sort of movement. So that is the tying down, right? It's the ties or anchors, right? Provides anchor force, right, to stop the downward movement of this big soil mass for this slope. So what is the detail for this enlarged things, right? So that is the anchorage. You can see here, that is, the sloping surface. So the slope, right? That's a slope. And you have, the, that's the, the air outside. And here's the soil, right? So you have to provide this anchorage, okay? Now this anchorage will have an enlarged end, right? Enlargement. This enlargement. Now, expect that the enlargement could be made by expansion of the, at the end of this anchor, right? By mechanical means, or even by a very strong grouting material, like cement grout, right? Which could be pressurized, right? To make this enlargement. So if you have a bigger enlargement, so you have a stronger anchoring force, right? Now you can see here, right? Here, for a ground anchors, for this part, you don't need any anchoring force there, right? Because the whole mass here, right, will go down. So there is no need for you to give any grout, right? You don't need any grout, right, between this, this steel rock and also the soil mass, because it will go together, right, with the soil mass. So you can have what we call the free anchoring. You don't need any grouting, right? Because any grout will be useless, right? Because it will be eventually go down with the soil mass. So in terms of structure, right? In terms of the mechanics, you don't need any grouting at all. But for the other part is the fixed anchor. Here, right? That's the fixed anchor. You need grouting, right? You have to provide, right, the strong support here, right, beneath the failure surface. That is the failure surface. So anything behind or below the failure surface, you do need the grouting, right, in order to give the strong support, right, to arrest the movement of the soil mass. Okay? And this is the anchor head. You know, that's the anchor head. Anchor head. So let me recap, right? A ground anchor consists of three things, right? The anchor head, the free anchor length, where you do not need any cement grouting between the steel rock and the soil mass. And then for the last part is the supporting part, right? The fixed anchor, where you do need the grouting, right? A complete grouting between the steel rocks and also the soil. Now, if you have installed a pre-stressing, right? Here's the pre-stressing. That's the word. Pre-stressing means you apply a force, right at the start, so that you have an active force there. Active force. In other words, before the slope start to move, you have already an active force there, right? So that's the pre-stressing force. So that will give you a very good, right, stabilizing force, right, which will be pressed beneath the failure surface. Now that will give a very stable supporting force, right, to keep the soil mass stable, right? So that will prevent any landsliding movement, the slope. So that is the pre-stressing force. Now here's the rock anchor. You know what's the rock anchors? Suppose right here, right, you have a very steep rock slope, and you have the jointing. You know the jointing, right? You know the rock is not continuous, right? It's discontinuous along some, you know, the bedding plane or some planes. So you can see here, right? This rock may go down, right? Because, you know, it's going to slide down, right? So we're worrying about this piece. So what you are going to do is use a rock bolt, right? Here's the rock bolt. The rock bolts. Set down, the rock bolt. Okay. So this rock bolt will anchor this piece of rock, right, from falling down, right? So that is the purpose of rock bolt. Of course, the rock bolt does not mean that it has to be pre-stressed because it's too expensive, right? So you just need to, right? Again, you have the free tension length, and then you have the, you know, the fixed bond length where you need grouting, right? So the encapsulation, right? You need the teeth there, right? The teeth to improve the mechanical support, right? And here you have the free length, right? So you don't need any inferior, right? You don't need any grouting here, right? But here you still use the grout. Why? To improve the corrosion resistance. You know, it's nothing to do with the structural strength, but it's having to do with the durability, right? You know, for any rock or the soil, right, behind a slope surface, you may have groundwater, and that groundwater may deteriorate, right, the metal bars, right, the steel rocks or the steel bolts. So you, in order to prevent the corrosion, so you do need some grouting, right? The grouting is going to protect, right, the metal surface from corrosion only, despite they are not designed to give the structural strength to support, right, any rock fragments. So it's typically about 25 to 40 mm and 3 to 6 meter long. You could have up to 10 tons. So that is the purpose of the rock bolts, to anchor the pieces of very loose rocks from falling down. Right? So in other words, you could have you do need a rock bolt there, right? A rock bolt there. So in order to prevent the loose rocks from falling down. Now here are different measures of the rock slope stabilization. Particularly, it's called the dentition. What's the dentition? Like dentition for your teeth, right? So you can see here the picture, the detail here, right? First of all, you have some, you know, some rocks, right? Some rock, so that you can maintain the seepage, right? You can have the drains, right? So the drain will provide the drainage for the water, right? Not here the direction, no. There's no drains to allow the water to go out there, but it will have very small, drain pipe here, right? A drain pipe there. We will collect any water, right, from above and nearby, and drain the water, right? As for this, for this plane, it's perpendicular to your plane, right? And then after you pack up these rocks, right, and then you have to, to drill a hole to install, a metal bar. Right? This is the reinforcement bar, and then you have provide the concrete, right? To provide the concrete. Okay, so this rock, if this rock is going to tends to go out, now that could be resisted by these pieces of the steel bar, right? The steel bar will be installed, right, down into a very sound rock, right? Good rocks that will go. It will give you that resistance, right? So it will prevent the downward movement of the rock above this point. Right? It's that what we call the dentition. Right? So you can see here, right? Dentition here, and then the rock anchors here, right? Rock anchors. Okay, and then here all along you have the spray concrete, a rigid concrete surface, right? Spraying the wet concrete. And sometimes you may have some small wet holes, the wet holes, the wet hole. So the water will go out, and the groundwater could come out, right? The wet holes. And because this is a fault zone, there's a large discontinuity right here. So you worry about the whole thing will come down, right? Will come down. So you have used this very strong, right? Lock bolt, right? To provide the anchor force, right? To stop this, right? The large rock mass from sliding down above the fault zone. Fault zone 係 east 斷層啊。Okay, I think I have finished the chapter 7 on the slope stability. So any question for this chapter? So any question for this chapter? Any question? Is that clear? No question? can you see the chapter 8 PowerPoint slide on your screen? Yes? Okay. Okay, chapter 8, earth retaining structures. What's an earth retaining structure? What's that? Now let's talk about the learning outcome of this chapter. Now after this chapter, right, you have to know how to identify the various types of retaining wall system. In other words, how many kinds of different retaining walls are there. And also you should be able to analyze and also design some common retaining wall system. Of course, we are referring about very simple retaining walls, right? Because there are so many different kinds of retaining wall. Some retaining walls are very complex, right, to deal with. We are not going to do those type, right, of very complex system. Now, the retaining wall are almost regarded as vertical or near vertical walls, right, that could retain a certain height of soil or rock. Of course, for very strong rocks, you don't need any retaining wall at all, right? Because the rock could stand up, right, for a certain height, and you don't need any additional wall, right, to support that rock slope, right? But for some situation, right, we could have very weak rock system. So you have to build up a retaining wall strong enough to retain those rock mass because of their inherent very weak strength, rock strength, very weak in mechanical properties. So you have to you still need a wall, right, to resist the rock pressure, right, the rock mass pressure. In other words, the retaining wall is designed to resist the horizontal forces. So that is the main issue, right? Okay. So the purpose of the retaining wall is to resist, right, the force exerted by the retaining wall. Now, of course, you may know what's that sort of the forces exerted by the soil. Remember, we have talked about the lateral earth pressure, right? Right, in the chapter 4 or chapter 3, right? You have the active pressure, right? coming from the back of the retaining wall, right? So you have the lateral earth pressure, right? You have the, the active and the passive, right? So the pressure will be giving rise to these horizontal forces. Whenever there's a wall, a very high wall, and you have a good, horizontal force, you try to overturn, right? Overturn the wall, right? By toppling, right? Or by tilting, right? By overturning, right? Overturning. Okay. Overturning. Rotating about the toe of the wall, right? Now that could be a very disaster, right? The result is catastrophic, right? 災難性 okay, catastrophic. So we have to design the retaining wall safe against overturning. Or sometimes the wall could be sliding, right, horizontally. Instead of toppling over, right, the wall could move, right, horizontally, right, under the horizontal forces. So we have to think about, right, how a retaining wall could be designed as safe, right, against such movement, right. So the retaining wall has to be designed for here, right, for the strength, and also there will be no movement, right, of the wall, right. What does it mean by the strength? It means there will be no cracks overstressing the material in the wall structure itself. Right? Now the retaining wall is not very effective, right, in terms of structural action. It's not very structurally effective to resist the, the horizontal forces. A wall should be a very good structure to transmit the vertical loading, like columns, like walls. They are very structurally effective in resisting the downward force, but not good for the horizontal forces. That's why the retaining wall has to be designed very carefully for any horizontal forces. And that is the major topic of the retaining wall, because the wall is not good, right, for resisting the horizontal forces. So that is the, the main theme of this chapter. Well, the geo guide, yeah, the geo guide 1, stress that the walls must fulfill the fundamentally requirement of the stability, whether stable or not, right? Is there any, overturning, any sliding, and so on, or any settlement of the wall? Regarding the, not only the movement, but also the stiffness, right? It means, right, the strength, right? Is there any overstressing in some part of the wall structures? Is there any cracking, right, in the wall structure? And also you have to design for durability, right? Durability. Say the wall could be lasting for 50 years, right? So you have to provide a structure that could be durable, right, for that sort of the design life, right? Then you have to think about the requirement, not only for the whole design life, but also during construction, right? So you have to provide the template, right? A temporary safety, right, under construction. Right? So the contractor may have to think about, right, what sort of the stability problem or any stiffness problem, right, during the construction. So if there should be some problem occurring, then they have to install temporary supports, right, during construction. And as you know, in the structural design, you have to deal with the ultimate limit state, ULS, and also the serviceability limit state, SLS. Right? ULS talks about the the structural strength, structural collapse of the wall, but the serviceability limit state talks about any cracking, deflection, and so on. Right? Now, for the discussion and for the learning outcome of this chapter, we will concentrate on the ULS, the ultimate limit state, right? Because we know that failure is always the first and the most paramount important question, right, on the safety of a retaining wall. Right? So we have to think about any collapse, right, any failure of the wall. Right? So we have to put the serviceability limit state aside, right? We will concentrate our discussion in the failure mechanism, right? How a retaining wall could fail, right? Are there any severe structural damage, right? Types of retaining wall, right? We have classified the retaining wall into here externally stabilized system or the internally stabilized system. What's the difference between the internal and the external stabilized system? Well, you have this classification. I could show you by drawing some sketches, you will know what sort of the system. Now, external stabilized system, what's that? The in situ wall, right? In other words, you have, this, right, gravity wall. So if there is a force there, you have, a very pretty heavy weight of the wall, right, to stop the overturning, right? So that is the gravity wall, simply by the weight of the wall, by weight. So you could have a very massive retaining wall, right? You can see here, right? A very heavy object there. Or you could have a cantilever. Now, cantilever means here, right? A very thin wall, right? And then you could provide some anchor there, say that was ship out, so that's a concrete wall. And you could have a steel ship out there, and also you can have an RC, a very thin wall, and also you have a very thin base, so that is an RC. In RC wall, you have to put up the reinforcement, right? Fix the steel bars, and then place the concrete, right, to finish this RC retaining wall, right? Okay, so reinforced concrete. And you could have the counterfort or buttress. Counterfort means, here is the wall, right? So you could have, here, right? Put up the buttress, right? That's the buttress, right? Triangular piece of walls, right? If the wall's very high, right, very high, So you have to provide, right, these triangular pieces of wall, the buttress wall. Now that is the external, right? Now you could have the internal one. What's that? So, right? So you have the, that's the slope, right? So you put the, this buttress wall behind, right? Behind the external wall. So the external buttress wall means the walls will be installed in front of the wall, but for the internal buttress, right? Internal buttress. Okay, it's completely, right, out of your sight, right? So that will be much more pleasing, right, to the user, right? It's much more neat and tidy, right? But of course, it will be much more expensive, right? Because you have to do, right, the construction of the buttress wall behind, right, behind the wall. So you have to excavate a lot of material, right, and then do the construction of the buttress, and then you have to backfill it, right? So it's very expensive, right? In Chinese, buttress wall, okay? And you could have the gabion, right? Gabion. Gabion means what? You use, right, steel wires, right, to make a cage, right, and put the rocks inside. So you have the rocks here, right? The rocks. All the rocks are packed inside a cage made up of steel wires, right? So that's the gabion wall. Okay. Now, what about for the in-situ wall? In-situ wall means, right, the ship pile wall. You know what's the ship pile? Yeah, right. You have the railing and strut, right? Right. Sheeting, ship piles, railing, and strut. A very common, what we call the cofferdam, right? Cofferdam railing wall. Okay. You could have the soldier pile wall, and even the, the diaphragm wall, and so on. Right? So you have to build the wall within the, the building site, right? But for the gravity wall, they are almost used for the road construction, right? Say here's the, there's the highway, right? There's the carriageway. Then you have to, complete a standalone concrete wall there, okay? So that it can stand still there and protect the vehicles and the pedestrians, right? But for the construction of building, right, same in basement, right, you're going to construct a basement, right, for a building, then you have to, to stabilize the wall there by installing all these railing and struts, right? Of course, you can have the cantilever, right, here, free cantilever. So you have to dry your ship pile very deep so that it can, right, it can be made stable, right, by the, a very deep penetration depth, right, depth of penetration, to make the ship pile become stable, right? And what's the base? Cantilever, right? That's the cantilever. What's the base? Here's the base, right? Because you have the base by means of the strut and the railing, or you could have the tie back system, right? What's the tie back? So you shift piles, and then we have the tie bed, right? Say you have the tie bed there, right? So that's the tie bed system. Okay, so we have discussed all these different types of the earth retaining structure. Now I will stop here for the lecture, okay? And we have some, say, a 10 minutes break before we come back for the tutorial, okay? So before the break, any question for the lecture? Any question? No screen? Sorry for that. Or perhaps I will repeat, right? Repeat this few slides, right, in the next lecture, okay? Sorry for that. I think I need to repeat, right, my discussion on this few slides in our next lecture. Is that okay? Sorry for that. Now I will repeat my lecture for these few slides in the next lecture. So no worry, please. Sorry for that. Take the break first. Can you see the picture and my voice and hear my voice? Okay. Now, okay. Now, in this evening, now we are going to ask you to watch some videos, right, on a laboratory test. You know, the outbreak of this virus, right, currently developed in the locally in Hong Kong. So we have to use the alternative, right, to do the laboratory test. Now, here's the direct shear test. Now, what's the direct shear test? Here's the shear box, right? So first of all, you have to know this word. It's a box, the shear box. The shear box contains of upper parts and the lower parts. Okay, it's a box. You know what's a box? A cube, right? Now the soil is retained, right, full inside the box, and the lower box will be motorized to move towards to the left, right here, and the upper half will be kept stationary. Okay, so anyway, there will be a relative displacement, right, or relative movement between the upper half and the lower half, right, of the soil inside that box. Is that clear? Can you follow? In other words, the mass of the soil in the upper part will remain at rest, while the lower half of the soil will be moving towards to the left. Is that okay? Is that clear? Yes or no? It means that, right, the soil in the upper part will be moving right. The two pieces will be moving relatively in the middle, right, by sliding or by shearing. Is that okay? Now let's take a look for these pieces. Here. Okay. Now let me draw. Okay. Okay. So that is the, you know, the upper part, and that is the lower part. Okay. This one is going to move towards the left. Relatively, it's moving towards to the right. Okay. So there is a meter, right? Here's the dial gauge here to measure the movement, horizontal movement, right? Delta H. Now, of course, when the lower part is moving towards the left, now it's possible, right? The soil, right, may move in the vertical direction. That's why we have, you know, to put a dial gauge to measure if there is any vertical movement of the upper part relative to the lower part. Okay? In other words, it's possible that, it's moving vertically and also moving horizontally, right? Delta H, and that is known delta V, right? Is that okay? So there are two dial gauges to measure the horizontal movement and also the possible vertical movement. Okay. Now there are two forces. The first force is the normal force, the normal force. Why is it normal? Because it is right angle, right, to the horizontal sliding surface, right? So it's called the normal or the vertical force, right? The normal force. And here's the horizontal shear force, right? S. So that's the normal force. Okay. So what's the normal force? Normal stress, sigma n, is equal to the normal force divided by the area, right? What's area? This area. Here, right? That's the area. What's the area? What's the area? The shear box area, right? Here for our test is 60 times 60. 60 mm times 60 mm. Okay. Now the normal force will be given, right? So we will apply a set of loading, right? So that will apply a normal force. Try to press the upper part against the lower parts, right? Now, of course, I think, right, you should be very, very aware that if n is higher or sigma n is higher, then the shear force will also be higher. And what's the shear stresses? The shear stresses is equal to what? Right? Shear, right? Is equal to what? Shear force over area. Okay? Same area. Right? So can you catch up with my explanation? All of you. So far, so good. Can you understand the experiment up to now? Yes or no? Half. Now, let me explain further. Okay. Here's your hand. You apply a normal force. And you try to move, right? You try to move in that direction. What will happen? There will be a shear force, right? You put your hand on the top of the table. Do you think if n is greater, your S will also be greater. Is that true? Is that true? Still half and half? Normal force and also the shear force. Right? The table is the lower part of the soil, right? And your hand is the upper part of the soil. When you press the two things together, stronger the pressing force, then you need a higher shear force in order to move. Is that right? Okay. So that is the purpose of applying a normal force, right, to the two pieces of soil, right, in the upper part and the lower part, in order to study when you apply different normal stress here, then you will obtain different shear stress. Is that true? Okay. In other words, we want to plot this graph. If that is the shear stress and that is the normal stress, we believe that, right, a higher normal stress, right, will give you what? A higher shear stress. Is that right? Bigger the normal stress, you have a bigger shear stress. Is that true? Yes or no? Yes, that's good. Now, that is the purpose of doing this direct shear test. We want to know the relationship between the shear strength against the normal stress. Okay? So you got 3 points, right? 3 tests, okay? In order to get a straight line, so test 1, test 2, and test 3, right? So you can have, once you got these 3 points, you will have a more Coulomb envelope, right? Failure envelope, right? So you got what? This is C, the cohesion, and that is the friction angle. Is that true? The shear strength against the normal stress. You will have the C and phi, right, from the lab test. Okay? Okay. Now, let me come back to our previous slide. Suppose this area is not true. Why? Because at failure, you can see the area is smaller than the original area. Is that right? The original area is across the width of the shear box. But here, at failure, right, further advancement of the shear box, you have a smaller area. Is that correct? Yes or no? Yes or no? The area in this denominator should be smaller. Is that right? Because you have, our contact. Two areas are our contact, right? Can you see? Could you imagine that area will become smaller after the movement? Come on, Only one got yes. Reply. What about the others? Two, three. Okay. So you should minus what? This area should be minus if the shear box here is the, is the width of the shear box is equal to B times what? It has moved delta X. So you have to multiply, right? That is the corrected area, right? What we call the corrected after the correction. B times delta X. Delta X is the movement, right? So the length will be, right? The length of the travel, right, will be equal to the width of the box, right, minus the movement. Okay, so that is you have to minus this correction. Okay. Okay or not okay or no good. Okay or not okay. 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 Now let me tell you some subtle things about this. Now at the beginning of the shearing, what will happen? What will happen? Under very heavy, well, very big, normal force, what will happen? When you start to, what will happen? You can see here, right? These three pieces. A, that's A, that's B, so that's B, right? The B will go a bit upwards, right? And this C, in other words, it has to climb over, right, the lower part. Imagine. When you're sliding, very dense, right? So it has to, right, to climb over, right? So that that's, that's the particle A, right? And the B, right? Here, right? Can you see the movement? I try to do some animation, right? Can you see the, the sequence of the movement? Can you see the movement? Okay. Now tell me, what's the difference between the two? When you go from this side to this side, there will be an increase in the volume. In other words, the delta Y, okay, the delta V, the vertical movement will go upwards, right? So the volume will be increased. Is that true? So the vertical movement is not going downwards. Instead, it will go upwards. Can you see or imagine that kind of movement? It's called the dilation, right? A very important concept, because the grains, the soil particle will will roll over, right? The lower one will roll over the lower soil particle. So in other words, there will be a upward movement, right? Or increase in the volume in this shear test, right? Can you imagine on that? In other words, when you plot, right? When you plot say if that's the movement, right? The time or the delta x, there will be increase, right? Increase before it go downwards, right? That is the delta v, right? The delta v will go firstly upwards, right? So there will be an increase in volume. Increase in volume here. Okay? Before it will go down again. Okay? So you should notice the dilation here. Okay? Now, here you got 3 tests, right? Remember that. So test 1. Sorry. Test 1. N1, right? Or the sigma N1. So the sigma N1. And test 2. So you got, the shear stress here, sigma tau 1, and then you have, the test 2, right? Sigma N2, right? And then you have the, a bigger, right? Sigma N3, right? Sorry. Okay. You got a bigger sigma N3, and you got what? Here, right? You got what? Tau 2, sorry, tau 3. Okay, so you got what? Sigma N3, that is sigma N2, right? Sigma N1. You got what? Tau 1. Okay, tau 2 and tau 3, right? Can you follow? Apply, increasing normal law, normal force, right? So you will having a higher normal stress. Okay, and you measure the shear stress. Okay. Now, if that's okay, then we will look at the video, right? Remember, there are two instruments to record, right? The, you know, the horizontal movement and the vertical movement, and also the load, right? The load, the shear force, right? How much is the shear force to slide, right? To keep the the upper part and the lower part sliding against each other. Okay. So can you see the picture? So there are three measurements, right? At a particular normal force, you have to measure the horizontal movement and the vertical movement and the shear force, right, required to shear between the two pieces. Okay. Your response, please. You understand the the experiment? Please respond. Right? Okay. Now, when you start the shearing, right? So that's the delta x, is going to move horizontally. Now, what will happen? The shear stress, right, or the shear force will become higher and higher, right, until it will go down. So the failure shear stress, so that is the shear strength, right? Here's the peak, right? So that is the peak, right? So peak is the shear strength, right, for sigma n1. Okay. For sigma n1, because here is the normal force throughout the test, so it will give you sigma n1. Okay, say for test 1. And then you come to test 2, right? Again, so you have what? A much higher, right? Because you have a bigger normal stress, so you get a, test that is the top one, and you have a what? Tau 2, right? So that is the tau 2, right? Okay, similarly, you have the test 3, right? You will have a higher shear strength because you have a higher normal stress. Okay. Now, for the equipment itself, you have for the the dial gauge, dial gauge. So delta X dial gauge, you can see from the video, one division is equal to 0.01 mm, right? Okay, and also for the, for the delta V dial gauge, the vertical gauge, you can see from the video, one division is equal to one division 0.002 mm. Okay, and of course for the load, right, the shear force, right, you also the dial gauge, shear dial gauge. Now you will have the information, right? It's equal to say 1.40 something, right? Newton. Right? So you have the, this transformation, right, between the division and the actual movement or the actual force. So you got this, right, data. And also, for the soil specimen preparation, you have the shear box, right? Shear box, you have, this is the soil, right, specimen. But here, between, right, the box and the soil, you have these two pieces. First of all, because it's going to slide in that movement, so you have to, some groove, right? In other words, it should be like looking like that, right? So that it will keep the soil, right, and provide the grip between the cover and also the soil specimen. Otherwise, the soil, right, will go together with the cap. So you have to provide the grip, right, the grip. So the groove here, right, the groove is to grip, right, to grip the soil during the movement. Okay, and also you have at the top there will be a, or even below, say here, you have also additional on the top of the, the metal plate, right? You have a porous layer to allow drainage of the water, right, during shearing, to allow the drainage, to let the water go out, right, go out of the soil, so that the loading will not be resisted by the water pressure, because any water under compression will be freely going out, will be allowed to go out. So there will be no water pressure, right, to resist the loading. Only the effective stress, right? Only the effective stress of the soil is measured, right? Okay. So probably you have the whole idea, right? Now I want to So tell me, can you see the video with the voice? Okay. So there is a simple introduction to the shear test, right? Now we come to the test equipment. So you have a brief description of the testing equipment, right? You got the shear box, you can see the loading frame, and you can see also the dial gauge, right, to measure, the vertical displacement, horizontal displacement, and also the shear force. Okay. So that give you a close up, right? A close up shot of the equipment, right? it's important that you have to apply a medium pressure to make the compaction of the sand sample inside the shear box. You try to not to use a much higher pressure, otherwise the sand will give you a very dense state, right? Now that could make the test result very misleading. Okay. You should see the you should see the direction of the groove, right? It's important to orient the direction of the groove perpendicular to the direction of the movement in order to make sure the soil within the shear box could be gripped, right, by the upper part or the lower part of the machine during the movement. Please note that the lower dial gauge measures the horizontal force, right? The shear force. So you can see the proving ring, you can see that is a circular ring, right? Which give you the force and also give you the measurement of the shear force. And the gauge in the upper part of this video is the device measuring the horizontal movement, right? So you can notice that the calibration between one division and the force as well as the and the horizontal displacement. Please take a look closely the relative movement between the upper shear box and the lower box. Okay, so you can see the clear, right, the displacement between the two parts. Well, that is the completion of the experiment. You can see the technicians are dismantling, right, the setup of the equipment. So I will not go into the details for this laboratory testing procedure as well as the specimen preparation and so on. Now you can review all this video from the blackboard. All those videos are already there, right? So you can view the video again and again as you like, right? Now I'm going to discuss with you the lab test report, right? And the analysis of the test. So let me open the relevant document to you. Now, can you see the test data? Can you? Okay. Now, just I have told you, you got 3 stages, right? First of all, you apply a smaller normal force. Now, what's the normal force here? The normal stress here is 50 kPa, right? 50 kilonewton per meter square. Now, and then for the time history, right? You start from 0 and then up to 5 minutes. You got what? The vertical displacement in the second column, and also the horizontal movement in the third column. Now, please notice that all these figures are the division, are the reading of the dial gauge. So you have to apply, right, the calibration factor, right, to work out what is the exactly millimeter of displacement in the vertical direction and the horizontal direction. Okay. And I recall that the horizontal dial gauge will have one division for 0.01 millimeter. And for the vertical dial gauge, it should be 0.002 millimeter per division. And then you have the proving ring. The dial gauge will give you the horizontal force, right, the shear force, and the loading rate constant is 1.401 Newton per division. Okay, you got this factor, right, to work out the force, right, in Newton, so that you can plot, right, the whole thing, the load against the time until you got what? The peak, right? Remember, first of all, you have a straight line increase up to the top and then down from the top. So you have to work out the peak, P-E-A-K, the peak stress, right, under the 50 kPa. And then you have what? The stage 1, and then you come stage 2 and stage 3. So you got what? So you got here, right? Stage 2, what's the normal stress? 100 kPa, right? And for stage 3, you got 300 kPa. So you got 3 points, right? 50 kPa, you got a strength there, a shear strength there. And for 100 kPa, you got another strength, and so on. So you got 3 points. So can you plot the curve or plot the straight line to obtain the cohesion and also the angle internal friction? So you got all these data. So each one of you, remember, right? Not the group work here. For the individual yourself, your good self, please do your own analysis and plot that curve, right? And report those data. Now, as I know, we will give you some guidelines for doing the report. Now, please observe these guidelines very closely, because I was told that there will be quite a high weighting on your lab report, right? In order to replace, right, the midterm test. Okay, everyone got the message? Now, all this data, all this video have been uploaded to the blackboard. So go over to the blackboard and obtain all the information as you wish. I'm sorry that I have the work overtime to keep you almost half an hour longer. I'm sorry for that, but I think I better finish up all this video and the laboratory test tonight. Okay. So any question? No? Then I have to say goodbye to you and good night.